Hi, my name is Subhashis Mohanty. Welcome. What you are about to view is an excerpt from a larger body of work on manifolds, differential geometry, measure, and intelligence, artificial intelligence. It begins at a point in the larger work where I have just established the Cauchy-Schwarz inequality for complex numbers, and at a point where I have already introduced the three vignettes in episode 1. Vignettes that my viewers, you, can use to decide if you would like to follow these chronicles. This video is an excerpt from Vignette 1, Mathematics. The use of advanced mathematics to solve new AI problems, improve existing AI solutions, and to shed light on AI's black box inner workings. Vignette 2, Python code, but really the AI development lingua franca du jour, which happens to be Python at the moment, directed towards solving math and other problems. And Vignette 3, lean code, but again, really the math formalization lingua franca du jour. So, mathematics for AI to help solve math and other problems, and the engineering, instrumentation, and formalization of mathematics itself. About the Cauchy-Schwarz inequality in this video, I have chosen this mathematical object from several possible ones that recur in various guises and complexities in parts of mathematics to enable me to tell an epistemological story involving mathematics, AI, and human capabilities. Finally, it is not essential to understand the mathematics in this video in order to appreciate the nuances I'm trying to tease apart between human intellect, will, creativity, collaboration, and AI. The mathematics in this video will be fully and rigorously explicated in a subsequent video. Meanwhile, kick back, relax, and enjoy a celebration of humanity. The Zeitgeist seems to believe that intelligence is in the bag, that intellect, human intellect, is going to be replicated shortly. And given the performance, the stunning performance of LLMs, chatbots, co-pilots, and the like, begrudging this belief is fraught with risk. And at first blush, even claims of passing the Turing test cannot be easily dismissed. And yet, there is more to it than meets the eye, as I shall try to motivate. Let us take the briefest of tours into the rudiments of text and image intelligence as warm-up, leading to a discussion of mathematical intelligence, our main focus. Starting with the word whereof, we can sequentially query a language model for the next most probable word. And here I am showing you the next three most probable words following whereof. And if we continue with this sequence, asking for the next most probable word, then we arrive at Wittgenstein's pithy aphorism. Whereof we cannot speak, thereof we must be silent. Predicting the next word, the next token really, is a simple though powerful idea, as we can see here, and is a foundational pre-training task in the learning pipeline of most LLMs. The format of this diagram is courtesy Chris Manning's Stanford CS224N course, Natural Language Processing with Deep Learning. You have a center word here, speak, and an outside context window of size n Here n is equal to 2 on the left and the right. And the question we would like to pose is, what is the probability of the outside context word, of an outside context word, given a center word in a large corpus of text? I have used the idea underlying this diagram to see if I could recover Wittgenstein's aphorism from a language model. And so I could. Simple idea, powerful result. Note that text intelligence is far more capable than mere next word or next token prediction. Sonnet composition, annual report analysis, code debugging, and much else. Let's next move to a brief tour of image intelligence. If you feed an image into a convolutional neural network, here VGG16 in this case, then we can extract the intelligence being built into the network layers. Here I'm showing you the last few layers of the network at a stage when the primitives, lines, curves, shapes, and shadows have already been extracted. Breaking down an image and building it up layer by layer allows a network to try and find a match for the image in its image list. And here I show you the output of the network, the three top matches: sunscreen, bathing cap, and sunglasses. Sunscreen here is off. There is something peculiar about this picture, that the three models I tried, VGG16, ResNet 18, and ResNet 50, all of them output sunscreen with a non-trivial probability. I'm sure this will be sorted out or has been sorted out in other models. Nevertheless, bathing cap is partially accurate given the similarity in shape to the beanie I'm wearing there in this picture at the Rodin Museum Garden in Paris, trying to strike the pose of the thinker, the poseur. Sunglasses is spot on with some probability of a match. Note that image intelligence is far more capable than mere object identification, text to image, image to text, and much else. With this warm-up, let's now move to a discussion of mathematical intelligence. Recall this simple proof of the Cauchy-Schwarz inequality a few slides ago. What did we do in the body of the proof? A whole lot of algebraic simplification. Machine algebraic simplification is a type of machine intelligence. And while it was already in the bag in the 80s with computer algebra systems such as Maple and Mathematica, coming up with the key that unlocks a theorem is something else. Here, starting with this key, this sum, we were able to arrive at that result. Seeing the key that unlocks a theorem has got to be another level of mathematical intelligence beyond simplification. Note, to be fair to Maple and Mathematica, they are more capable than mere simplification, being full-featured computer algebra systems, and can verily be regarded as being members of the corpora of machine mathematical intelligence. Next up, we have the Cauchy-Schwarz inequality for square-integrable functions. V is a set of functions from the reals to the set of complex numbers, each of which is square-integrable, meaning that its absolute value squared integrated over all space is finite. If we endow V with an inner product and a norm, then we get the Cauchy-Schwarz inequality for square-integrable functions, the technical details of which we will cover in the sequel. So here we have the Cauchy-Schwarz inequality for complex numbers, and there we have the Cauchy-Schwarz inequality for square-integrable functions. They are identical in structure and spirit, except for sums and integrals. To create a mathematical object like the inner product space featuring the Cauchy-Schwarz inequality and other properties and applied identically to finite dimensional vector spaces and infinite dimensional vector spaces has got to be yet another level of mathematical intelligence beyond algebraic simplification and coming up with the key that unlocks a simple theorem. Next, we cross over from mathematics to physics, from deep within harmonic analysis to quantum mechanics to the Heisenberg uncertainty principle. Psi x is the probability distribution of the position of a particle. Psi x is square integrable because its absolute value squared integrated over all space is finite. Mu x is the mean of the distribution. A word on notation. We use uppercase random variable when we're talking about the constants of a distribution such as mean, standard deviation, and variance, and lowercase when we're talking about particular values. The quantity to the right of that is the probability density of the distribution, and the probability density integrated over all space is equal to 1, satisfying one of the axioms of probability theory. The probability that you will find a particle somewhere is equal to 1. What is this integral? Well, it is the definition of the expectation of x minus mu x quantity squared. And what is this expectation? It is the definition of the variance of the distribution. And what is the variance? The variance is a measure of the uncertainty in the distribution. So, this integral is the uncertainty in the position of the particle. Moving over to the factor on the right, we have psi hat. Psi hat is the Fourier transform of psi. So psi hat is the probability distribution of the momentum of the particle. And since this integral is identical in structure to this integral, what we have here is the uncertainty in the momentum of the particle. So on the left of this inequality, we have the product of the uncertainty in position with the uncertainty in momentum. And that product is bounded below by 1 over 16 pi squared at Planck scale, where Planck's constant h is equal to 1. You might have seen the Heisenberg uncertainty principle in this format in blue here. The product of the standard deviation of the position random variable and the standard deviation of the momentum random variable is bounded below by h over 4 pi. These two inequalities can be reconciled by taking cognizance of the fact that the standard deviation is the positive square root of the variance. And so, if we take this inequality and square it, substituting h is equal to 1, we get the inequality in the previous slide. The derivation of the Heisenberg uncertainty principle, a profound result in physics, is quite technical, and we will need to cover a lot of ground before we come to it. But come to it we will. Meanwhile, I should like to tell you that the ingredients that went into the derivation of this result include the properties of the Fourier transform, Plancherel's formula, and in a recurring theme, the Cauchy-Schwarz inequality. The Cauchy-Schwarz inequality for square integrable functions in this case. Let me move these boxes around so that they are all visible and I have a little more to say about them. Let's recap. We started with the Cauchy-Schwarz inequality for complex numbers, traveled through the square integrable version of the inequality, crossed over from mathematics to physics, and arrived at the Heisenberg uncertainty principle, a foundational result in physics. the magnitude of this intellectual jump, the magnitude of this human intellectual jump has got to be within the ambit of AI's ambitions if the claim is to be made that intelligence is in the bag. Let's discuss that a little. Consider this epistemological journey from the Cauchy-Schwarz inequality to the Heisenberg uncertainty principle. The knowledge stack behind this epistemological journey includes set theory, topology and analysis, manifolds, harmonic analysis, geometry, classical mechanics, and quantum mechanics. Note, this stack is not necessarily chronological, and neither is it indicative of the strict dependence of a higher level box on a lower level box. And different physicists and mathematicians are likely going to organize this slightly differently based on their taste and focus. The salient features of this epistemological journey includes nearly 5 centuries of sustained human scientific and mathematical development and progress with a burning will, a burning human will to understand nature, and a matching human will to understand and create related logical structures. It includes stupefying creativity, stupefying human creativity in support of a burning human will, the creation of a large number of new branches of mathematics and physics in support of the enterprise. And it includes peer advocacy, peer convincing, and peer review, distinctly human traits. It'll be interesting to see how humans and machines cooperate to capture these historically essential human traits: will, creativity, and collaboration, to understand more of nature, to expand the horizon of logical structures, and to understand even intelligence itself. I have one more page to add to this story, which comes next. There is a fair bit of glorious mathematics in the next few slides. And in the fullness of time, we will have an opportunity to savor those glorious nuggets. But meanwhile, let me press on with the discussion of mathematical intelligence. In 1854, German mathematician Bernhard Riemann presented his complete and rigorous theory of integration to the faculty at the University of Göttingen in Göttingen, Germany. 1854 was a watershed year for mathematics, as it unleashed a fertile period of development in the theory of functions. And yet, chinks appeared in the armor of the Riemann integral. Here follow 3 such chinks. Consider the Dirichlet function defined on the closed intervals 0, 1 to R, which is 1 on the rationals and 0 on the irrationals. Every neighborhood of every point in the domain of this function contains both rationals and irrationals. And so this function is continuous nowhere. And since this domain is uncountable, there are an uncountable number of discontinuities in the function. And thus, this function is not Riemann integrable, because the Riemann integral can only handle up to a countable number of discontinuities. Chink. The Fourier coefficients of a square-integrable function, integrable in the Riemann sense, form An L2 sequence, a square-summable sequence by Parseval's identity. And yet, there are square-summable sequences whose terms are not the Fourier coefficients of any Riemann integrable function. Ideally, we would like to have a correspondence between square integrable functions and square summable sequences. Chink. Coming to our third item, consider this sequence of Riemann integrable functions. Every function in this sequence is Riemann integrable. And its limit, if it existed, would have to be f. But f is not Riemann integrable since it is unbounded. It is unbounded near 0. And so, the space of Riemann integrable functions contains sequences whose limit is not in the space. And thus, the space of Riemann integrable functions is incomplete. Chink. Fast forward to 1902, 48 years later, when French mathematician Henri Lebesgue presented his theory of integration at the University of Nancy. The Lebesgue integral does not suffer from these limitations and matches the Riemann integral wherever the Riemann integral is feasible and can integrate a wider class of functions. The leap from the Riemann integral, the lofty leap, the lofty human leap to the Lebesgue integral, and all the paraphernalia it sucks in, square integrable functions, square summable sequences, Fourier analysis, must be within the ambit of AI's ambitions if the claim is to be made that intelligence is in the bag. This brings our current discussion of mathematical intelligence to a close. Part 2, 3, 4, or more will be in the sequel.
Thank you.